Get started. So today's lecture is going to be introducing the concept of production. This is something that you guys should have already been familiarized with just through lecture and through section, but I'm going to try to give you guys as much of a recap as possible and maybe cover some points that maybe you guys don't quite feel comfortable yet. And so that's going to lead me to Wednesday. So I know that you guys have your midterm Thursday morning. I know that last midterm, it was kind of unfortunate, the timing of it, just having it be right after Veterans Day, or yeah, right after Veterans Day. So I wasn't able to present on last Wednesdays or on the Wednesday of that week. But hopefully we can get a good review in tomorrow or 2 days and get you guys feeling pretty good about the midterm. So the deal with production, and hopefully you guys have started to kind of notice, is that we treat production very similar in the way that we choose or that we treat consumption, in that a lot of the concepts carry over, right? So if you felt pretty good about stuff in weeks 1 to like 3, I think that at least for cost minimization, there's obviously more material that won't be covered in this coming midterm that I'm not going to introduce quite yet. So right, we're going up until cost minimization. So through the concept of cost minimization, I think that applying knowledge of weeks 1 to 3 is going to be very important. And hopefully if you guys are familiar with that, you'll be familiar with this, right? So the idea is that we have firms that are able to produce goods based on inputs, right? So they take 2 inputs, and so we assume that they only have 2 inputs. They take 2 inputs and they produce a good, right? So for example, a desk might be composed of wood and nails, right? So the wood and the nails are 2 inputs. They each have a cost, right? And you take those 2 together and you create desks, right? So we have something called a production function. So the production function is going to look something like this: f of x1 and x2. And we're going to say that this is equal to y, right? And so hopefully you guys are starting to see the pattern, right? With consumption, we were measuring utility, but now we're just measuring straight output. How much can we produce? So y is production, given that we have 2 inputs, x1 and x2, right? And the cool thing about the production function is that we get these, I hate to say function again, but we get these functions that are really similar to what you guys have already noticed, right? So we have a min function, so we have perfect complements, right? And this can maybe go into the desk and the nails example, right? The wood and the nails. You need a set amount of each good for to create one desk, right? So we're going to notice that this is going to be a min function, right? We also have perfect substitutes, right? Your classic x1 plus x2. And we have obviously our Cobb Douglas, right? And that's going to be just x1, x2, okay? So the production function works exactly in the same way that the utility function works, right? And so if you kind of remember that utility functions corresponded to indifference curves, we're going to have it that basically the same is going to be true, right? So utility, this marker is weird. Utility function, right, corresponds to indifference curve, and I'm just going to abbreviate that IDC, right? In that same exact way, the production function is going to correspond to what we call an isoquant, right? And so we're still going to have our x1 and our x2 axis, right? Good 1 and good 2, or I guess in this case it's input 1 and input 2, right? And in that same exact way that the indifference curve worked, we're going to have, right, so this would be like a min function, right? But basically the idea is that everything along this curve is equal to y, right? Meaning that no matter where you are on this isoquant, we're producing the same amount of output, right? And so because of that, we're going to have, right, a similar notion of, right, it was marginal rate of substitution, right? That was the slope of our indifference curves. And we're going to be introduced to the concept of technical rate of substitution, which is really kind of lazy, right? They couldn't really think of anything much more creative. But this idea of a technical rate of substitution is going to be the ratio of the marginal products, which I'm going to get into just real quickly, right? So kind of like how the indifference curve worked, we could have isoquants that look like, right, what I just drew. They could also look like this. And most commonly, they're going to look like this, right? The downward sloping, diminishing products, right, that we've seen before. So our classic Cobb-Douglas that we're going to be able to perform nice, clean calculus with, okay? And so remember that each point along this this curve is going to be the same amount of production, right? It produces the same units of goods, okay? And so kind of like how we had marginal utility, we're going to have the concept of marginal product, right? And so if you're familiar with marginal utility, right, how it was the increase in utility, keeping one good constant and increasing another good by one, right? That's going to be exactly true for marginal product. It's going to be the increase in production from holding one of the inputs constant and increasing the other by one, right? So in terms of notation, we're going to see something that looks like this. So the derivative of the production function with respect to, say, input one, right? So this would be the marginal product of input one, right? And we're also going to have the marginal product, right, of input two, right? And so if I had, say, f, and actually let's just do this over here. If I had, say, f of x1, x2 equals x1, x2, right? This is my production function, and I'm taking it with respect to good one, or input one, right? So that'll just be x2. And if I'm taking this same production function with respect to input two, this is just x1. And so you'll notice how, right, if you kind of remember when we were talking about consumption, and let's actually bring this over here, right? Our MRS was equal to the ratio of the marginal utility of good one over the marginal utility of good two. And nothing's changed except that instead of calling it marginal rate of substitution, we're going to call it technical rate of substitution, right? So instead of an M, it's a T. And this is just going to be the marginal product of input one over the marginal product of input two, right? And in this case, this just becomes x2 over x1, right? And so this should all be kind of very familiar to you guys, right? And it should be a good refresher, right? We're using the same concepts, but we're applying them to different applications, okay? So this is kind of just a quick review. Here's something that is somewhat of a new concept. You've seen it before in the form of scalar invariance, right? Or it was called also homogeneity of degree zero. But this time, the application is going to be for returns to scale, right? And so why do we think returns to scale is an important concept, right? Think about it in terms of a business, right? We're looking at a business and we want the business to grow. So the way that we would grow is by using more inputs, right? You have to spend more to get more. That's kind of the idea of businesses. However, you want to see whether the amount that you're spending is resulting in greater profit, right? So kind of what I mean by that is, say that it takes you So say that you have a restaurant, right, and you want to branch out. And so the restaurant that you have right now uses, say, 5 cooks and 2 waiters. And so you want to see whether doubling the size of your staff is going to increase the amounts that you can produce, right? So instead of having five cooks and 2 waiters, does having 10 cooks and 4 waiters result in greater profits, equal profits, or less profits? That's kind of the idea of returns to scale, right? And so the way that we test it is we see whether we have a ratio. And so let me just kind of write this out. So this is our production function, and we're going to multiply each of our inputs by some constant t, right? If you'll remember with scalar invariance, which we use to test demand functions, we were using some constant lambda, right? It's the same concept, just a different constant. Yeah, it's kind of wordy. Okay, right? And so we want to see how this compares to if we just multiply our original production function by that same constant, right? And hopefully you guys can see how these could end up being different than this, right? So this is just some number, right? This is just some number value, right? It's a value that's a function of inputs, right? But it's just some number. So essentially, and I like to think of t, I like to think of t as being 2 because it's really easy to kind of conceptualize the idea of doubling something. But really, realistically, t could be any number between 0 and like infinity, right? But I think that just in practical use, having t be equal to 2 is the best idea. So what we want to see is when we double both of our inputs, right? How does that compare to just multiplying how much we were producing before by 2, right? So if you think of something that has constant returns to scale, right, then this should be equal, right? You double your inputs and you double your production, okay? But that's not always the case in business, right? Because it's possible that when you double your inputs, you can more than double your production, which is obviously ideal because when you double your inputs, you double your costs, right? But when you more than double your production, you're more than doubling your revenue. And we know that profit is revenue minus costs, right? And so, right, let's say that we were making $10 and it was costing us 5, right? But now when we double our inputs, our cost goes to 10, but say our revenue goes to say 22, right? We're now creating more profit for ourselves, okay? So that's kind of the idea. Does that make sense to you guys? Like you're more than doubling your profit in this case. And so given that this equals constant returns to scale, right? Something that would create increasing returns to scale would look like this. So this is constant, right? This would be increasing, right? And this would be decreasing. And so you never want to have decreasing returns to scale because it means that you're actually not getting what you should in return for your inputs, right? You're actually getting less profits out of your inputs than you normally would. Okay, so that's kind of the idea. You can apply this to your production function, and this will always be true. But with Cobb-Douglas production functions, you're going to notice that there's like a really easy trick that you guys can use, right? So generally with Cobb-Douglas, so this only applies to Cobb-Douglas, right? We know how our production function looks something like this, right? A, x1c, x2d, right? If c plus d is equal to 1, we have constant, right? If c plus d is less than 1, we have decreasing, right? And if c plus d is greater than 1, we have increasing, right? And remember, this c plus d corresponds to the exponents of the production function, okay? So given all that we've learned so far, I want to talk to you guys about how we're actually going to minimize our costs, right? Given this, um, given this information, right? And so cost minimization is kind of dependent on the time frame that you're working with. So for midterm 3, we're going to assume everything is in the long run. And so what does that mean to be in the long run, right? Well, in the long run, right, we're going to say that all costs are variable, right? Meaning that you have the decision of whether to incur those costs or not. And so think of labor, for example, right? If you're a business, and this is like in the most theoretical way possible, Kyle, that was increasing. Yeah. So think of like labor, for example, right? A restaurant has um, employees that it obviously has to staff, but you can control the schedule on a week by week basis. And so in that sense, the cost of labor is variable, right? But for a business, and more specifically, I think the restaurant example is like the easiest to kind of think about. More specifically, right? There's also going to be costs that are not variable. And so in this case, when costs are not variable, we call that period the short run, right? Where we have some fixed costs, okay? And so we call these fixed factors, right? And these are variable factors, right? It kind of goes with the name, right? But essentially, think of stuff that are fixed, right? Like a lot of you guys, and I'm not sure about whether you guys are doing it now, but a lot of you guys live in IV, right? Where your monthly payments are fixed, right? Because you signed a contract. And so those are costs that you have to pay whether you live there or you don't, right? Which is why some people get subleasers, right? So in that scenario, those would be fixed factors that you have to pay no matter what, right? And so when you apply it to the restaurant example, fixed factors are kind of costs that you have to pay no matter how much you produce, right? Whether you produce 1,000 units or 10 units, the cost is going to be the same. And so this is typically associated with like leases on a building, right? So businesses have the option to rent out a building space for a year, 5 years, 10 years. I'm not really too familiar, but all I know is there's a fixed time in which they actually have like ownership, or I guess not ownership technically, but where they are in possession of the building. Okay, and so those are fixed factors. And so we say that, right, in the long run, none of those factors are fixed anymore, right? So say you sign a 1 year lease in IV. After that year, you can decide whether you want to rent again or you don't, right? But either way, you're not tied to that until you decide to rent again. Okay, so that's kind of the difference. Hopefully, it makes sense. Although I do know that there are times in which it can be confusing whether something is a long run or short run scenario. Okay, um, but we're going to assume that we're in the long run for cost minimization sake, and assume that all costs are variable, right? Meaning that we don't have a fixed input, um, which we'll see starting next week. And you guys have probably already seen it in your lectures, okay? So on to kind of the meat and potatoes of what we're going to talk about. This is going to be cost minimization, right? And so I want to kind of bring you guys back to the profit model that I briefly wrote down. And so it's possible that you guys didn't even notice that I wrote it down. But in this class, right, we're going to make the assumption that profit is going to be equal to the price that we sell a good for times the amount of units that we produce, right? And so the reason I write it in this way, right, this is equal to y. But the reason I write it in this way is because I want to show you guys that how much we produce is a function of however many units of input we're going to decide to utilize, okay? And so this is, right, price times the amount that we sell. This is our revenue. And we're going to say that this subtracted by the cost is going to be equal to our profit, right? So cost is what we call W1 X1 plus W2 X2, right? And so this is equal to C, right? And so hopefully you guys are familiar with the notation here, but just as a refresher, W1 is equal to the cost of X1 and W2 is equal to the cost of X2, right? And this corresponds pretty well to P1 and P2, right? Which were the prices of good 1 and good 2, okay? So here is our profit model, right? In the sense where we have P times Y minus C is equal to how much net gain we have, right? And so I want to briefly introduce you to the concept of the ISO cost, right? So we already have been introduced to the ISO quant, right? Remember, ISO quant is basically anywhere on the ISO quant produces the same level of production. And so for the ISO cost, anywhere on that ISO cost costs the same amount of money, right? So let's look at the ISO cost, right? And so our axes are going to be X1 and X2 again, right? And we'll see briefly how we're going to put these two together, right? We have an ISO cost. Sorry, that was kind of just bumpy and I didn't like the way it looked, right? ISO cost is also on the X1, X2 axis, right? And basically, it's going to look something like this, where it's linear, right? Where this is a certain amount that we're going to incur in terms of costs, right? Meaning that any combination of X1 and X2 that is on this line costs the same amount, okay? And if you guys are wondering what the axes are, right? This is going to be C over W2, right? And this is going to be C over W1, right? And you guys can kind of see how this, right, was M over P2 in the case of the budget constraint, and this was M over P1, right? So a lot of this has a lot of like different overlap. The one thing that is true though is that if you remember when we were talking about week 1 to week 3 stuff, that there was one single budget constraint, right? Because your income was fixed at some amount that you couldn't go past, right? Yeah, exactly. Isaiah, that's exactly how you want to think of it. The one difference though is that the ISO cost, right, is not unique to a single level of C, right? Because if you think about it, right, M in the case of the budget constraint, M was fixed because we can't just have like increasing levels of income, right? Because that's not realistic. However, you can decide how much inputs you really want to choose, right? The amount that you can lose in terms of cost is infinite, right? And so basically, there's going to be different levels of C that are existing, right, on this X1 and X2 axis, meaning that we have infinitely many ISO costs, right? And so here, let's just draw all of them as straight lines, right? Basically, there's no limit to what our cost is going to be. And so there's going to be infinitely many of these lines, right? Cost could be $10. Cost could also be $10.49. It could also be $10.50, right? Right? There's all these variations of costs that are going to form basically infinitely many of these lines. And you kind of just, you separate them so that it's clear, but real, like, in the sense, like if it was drawn to like scale, there would basically be no gap between these lines because there's infinitely many of the lines, okay? So how do we how do we choose a profit maximizing level of inputs, x1 and x2, when I have a variable ISO cost and I also have a variable ISO quant, right? Because if you remember, there's also infinitely many ISO quants, just like there were infinitely many indifference curves, okay? So that's kind of a conundrum that you don't have to worry about until we get to next week's stuff, right? Where concepts such as the first order condition, right, are going to kind of kick in, right? Marginal cost is not something that you really have to worry about yet, but marginal cost becomes really key when you have to make a decision as to how much you want to produce, right? But that's not going to be midterm 3 material, so I'm not going to introduce it, but it's something that you should be cognizant of, okay? So when it comes to cost minimization, the kind of difference between cost minimization and stuff that's going to be on the final is that cost minimization, so cost min, right, assumes a fixed y, right? And so what does that mean, right? It essentially means that my ISO quant is going to be fixed, right? Meaning that I have a specific ISO quant that looks like this, and this is the only ISO quant that matters to me, right? And so if you think about kind of another way that you can kind of think about it is that this revenue, right? My revenue is already known to us, right? Because we know what P is, and if we know what the ISO quant is, right? It basically tells us what our production is, which means that we already know what revenue is going to be. And so if you think about what cost minimization means, right, in the sense of this context, right, when we have a fixed level of production, that essentially means that cost minimization and profit maximization are the same exact thing, right? Because if you kind of think about, right, profit equals revenue minus cost, right? If revenue is fixed at some level, the only way to make profit as great as possible is to make cost as low as possible, right? So in this case of cost minimization, right, they kind of go hand in hand when we have a fixed level of production, right? And you'll see that we don't always have a fixed level of production, but for now, we're going to assume that we do, okay? And we're also going to assume that x1 and x2 are variable, meaning that we can choose the level of inputs that is going to make producing y, right? And y is production or output, that makes producing output as cheap as possible, okay? And so, yeah, that's kind of how we're going to approach it. And so we're going to see an example, right, that kind of hopefully puts this into perspective. I haven't looked at the problem set from this week. Considering it's like week 9, I don't think it'll be because, yeah, I think it's just for the final, just because the way that they set it up, there used to be only 2 midterms, and so week 9 stuff would have already been past the last midterm. So it should be final stuff. There might be some overlap between midterm 3 and the final, but not all of it will be on midterm 3. Okay. So kind of given what we have here, right, we know that we have this isoquant, and I wish I had different colored markers, but we have this fixed isoquant, and so we want to be basically on the lowest ISO cost, right, that touches this isoquant, right? So that's going to be, I'm going to just draw it as best I can and pretend they touch, just pretend. Basically, this is the ISO cost that we're going to want to be on because it is tangent to the ISO cost, right? And so we've already kind of familiarized ourselves with tangency, right? If we have, say, a Cobb-Douglas production function, it's basically just going to be x2 over x1 equals the cost ratio, right? So this right here is my TRS, and we're going to set this equal to the cost ratio, which is going to be W1 over W2, right? Or I guess in this case, it's like negative, or it's like negative, negative, and negative, right? So we've already figured out what it means to be at a tangency point. We're going to set these two ratios equal to each other. But how do we ultimately decide what x1 and what x2 should be? Okay. So with that being said, I'm going to produce a example that hopefully makes it a lot more clear. But just before I do that, are there any questions about anything so far? All right, I'm going to take that as a no. So let's say that we have a production function f of x1, x2, and we're going to say that this is equal to x1 squared times x2 to the fourth, right? We are set to produce 100 units, and the cost of our inputs are 2 and 4 respectively, right? Meaning that this is cost of input 1 and this is cost of input 2. Okay, so how do we approach this problem, right? Well, we want to find essentially this, we want to find these values, right? And I'm going to write them in terms of their parameters, right? But essentially all this means is that x1 is a function of the price of the inputs and the amount that we produce. That's all it really means, right? But this is what we're interested in, right? Also, you guys should definitely get ready to see a lot of this notation where like they write stuff as a function of other parameters, right? So don't really get confused about that. All it means is that this is basically not some like static number, that it's a function of these things, okay? So we have our x1 and our x2, and that's what we're looking for, right? The first step is going to find our TRS, right? Kind of like material in the past, finding your MRS, right, was always a good idea. Finding your TRS is no different. And so we're going to say that this is equal to, right, 2x2 over 4x1, right, which means that this is x2 over 2x1, right? And so this, because we have, I guess, diminishing marginal product, so it used to be diminishing marginal rate of substitution. I guess if we have diminishing marginal rate of technical substitution, then I guess that's like the test. But basically, the test is still the same, where if we increase x1 or we decrease x2, then our TRS should also decrease as well, okay? Which we can see that it does. All right, so we have diminishing technical rate of substitution, which means that we can set this equal to our cost ratio, which is just going to be W1 over W2, right? Which is equal to 2 over 4, all right? And so with that information, right, we can basically just cross multiply, and we get 4x2 is equal to 4x1, meaning that x2 is going to be equal to x1 at our cost minimization point, right? Which is also the same as our profit maximization point, because we already know what our revenue is going to be, right? So how do we actually come up with the answer for this, right? In the past, we would plug this into our budget constraint, but we can't exactly plug it into our like cost equation, right? So just to kind of formalize it, C is equal to W1 x1 plus W2 x2, right? Just to formalize that. But because we don't know what the cost is, right? If we were to plug either of these variables into here, right? This would be kind of open-ended in that we wouldn't be able to come up with an actual number, right? Because we're still going to have C be an unknown variable. So we'll have two unknown variables, which is going to lead to a dead end. So we can't plug it in here, but where can we plug it in? Well, we already know that y is equal to 100, right? And so we have been given that f of x1 comma x2 is equal to y, right? And so y is equal to 100, right? But we also know that this is equal to x1 squared times x2 to the fourth, right? And so because we know what x2 is relative to x1, we can plug one of these variables in, and I guess it doesn't really matter, right? But we have x1 squared times x, and this is x2, but we also know that it's equal to x1, right? So this is like this, plug that in there, and the exponent stays the same, and so we get that this is all equal to x1 to the sixth, right? And so x1, if you were to kind of solve for x1, is going to be equal to 100 to the 1/6, which is equal to x2. All right, and so this is kind of similar to finding point B on a substitution and income effect problem, right? Because you basically have to set it equal to the utility. Just in this case, utility is production, right? Are there any questions about this, right? And so I guess if you wanted to finish off the problem, you could say that cost is equal to 2 times 100 to the 1/6 plus 4 times 100 to the 1/6, right? And whatever this value is, you don't really need to figure it out. Whatever this value is, this is going to be basically the lowest ISO cost that touches my technical rate of substitution, right?
Can you keep the board up, please?
Oh, let me just point my laptop down a little bit. Is this better?
Yeah, thanks. Oh, yeah.
All right, awesome. Yeah, okay, cool. So basically, if you wanted to visualize what this looked like on our x1 and x2 axis, right? We have a production function, and this is equal to 100, right? So any combination of x1 and x2, if you multiply, if you basically did this application, right, that would get you 100, right? So that's kind of what it is. So like, for example, if we had 10 units of x1 and 1 unit of x2, that would equal to 100, right? So that's kind of the thinking. And so we have this, and this stays here, whatever like the circumstances are, right? This is stagnant. You basically want to find the cost that is going to be, this is drawn really badly, right? So here's our production function. You basically want to find the cost, right, that is tangent to our production function, okay? And so this is equal to C, this line right here. Okay, does everybody get that? Or I guess, does everybody get that? It's a bad question, but are there any concerns or maybe things that you were unsure about with this?
Where did you get the C equals 2 times 100 to the 1/6?
Yeah, that's a good question. This is basically just the total cost, right? Which is W1 times X1 plus W2 times X2, and I've already just filled in the values of W1 and W2. Did that answer your question?
Yes, thank you.
Okay. So let's think about how else we can go forward with this. That was like the bulk of my lecture. And so I know that I usually go long, but this was kind of on the shorter side, and I don't really want to introduce that much more new material, just because I think that it'll distract you from the midterm. So are there any questions about this lecture? Or let's see, what was last week's lecture? Last week's lecture was like taxes and deadweight loss and all that. And then the lecture before was expected utility. So are there any questions about either, or I guess any of those topics?
Wait, so was this lecture not pertaining to the midterm?
No, this is the last material that will be covered on the midterm.
Okay, thank you.
Yeah, so basically doing the same exact problem, but with a non-Cobb-Douglas equation. All right, so I'll talk about diminishing marginal product just real quick because um, it'll be uh, a little bit less bulky than doing another problem with like perfect substitutes, for example. So let's see. We we have right. So marginal product is equal to the derivative of our production function with respect to a certain good. So let's say that it's with respect to good one, right? We know that our TRS is equal to MP1 over MP2, right? And so diminishing marginal product means that this ratio goes down as x1 increases or x2 decreases, right? And so this is exactly the same concept as diminishing marginal rate of substitution, just in the context of production, right? Did that answer your question? I know that it was kind of a shorter explanation, but I want to make sure that it kind of answered what you were talking about.
Yeah, the lecture told us not to confuse it with something. I think they were talking about diminishing TRS.
Okay, so it's possible that I'm confusing what you were asking about. Um, well, anything that has diminishing marginal product is essentially uh, as so anything with diminishing marginal product, right, is referring to, I think, probably the second derivative. So um, if you have diminishing marginal product, the second derivative is going to be negative, right? Because increasing x1 is always going to increase my level of production, right? So let's say that, just for a quick example, let's say that f of x1, x2 is equal to just x1, x2, right? Because we know that this is going to have diminishing marginal products, right? So here is my production function, and I want to find does x1 have diminishing marginal product, right? And so I think that this kind of has to do with the idea of like the different types of people with respect to insurance, right? How they have diminishing returns on wealth, for example. And so if we take a look at this, we know that the first derivative is going to be positive, right? So let's just actually just do this. So x1, so derivative of x1, x2 with respect to x1, that's just going to be equal to x2, right? And so basically x2 is always going to be some positive number, right? Because x2 can't be negative. You can't have negative inputs. So this is positive, right? But when you take the second derivative of this, right, with respect to x1, this will be 0, right? Meaning that essentially, as you kind of find like the slope of it, right, you're no longer going to be getting any sort of production from with respect to x1, right? And so how does that how do you think about this intuitively, right? Well, um, holding x1 constant, right? Basically, the only thing that affects my production is x2. But if I were to do that step again, right, with respect to x1, right, we know that this is 0. So essentially, we are increasing in x2, but by a constant amount, right? Does that, here, let's see what is going on in the chat. Yeah, it would be. Hold on, let me think of a better example. And so I may not have my definitions correct, um, but I believe it's something along those lines of you would probably take the second derivative of something. And so um, I could probably look into that a little bit more, but I think that the idea is the same. I probably didn't choose a production function that worked well with it. Um, but I think this is like the same idea, right? Where you're basically going to check the second derivative to see whether we have like a diminishing return on this like good, right? Um, so yeah, I'm not sure. That
Oh,
probably didn't
thanks.
answer.
It did a little bit. I'll go back and check the notes, but I'll drop in your hours. I'll drop into your drop-in hours to
Okay,
ask
yeah,
more.
perfect. And I'll read up on that a little bit more too. Um, but yeah, it's like the same idea as that. And so let's go to Becky's question about a like subs example of cost minimization. So if we have, let's say, f of x1, x2 be equal to 2x1 plus x2, right? This is a perfect substitutes question. And we say that y is, let's say, 100 again, right? And we have that w1 is equal to 5 and w2 is equal to 2, right? We want to see what is the cost minimization or cost minimizing way of producing 100 units, right? So kind of like how we would always do it, right? I mean, there's many ways of doing a perfect substitutes question, right? But the way that I've always kind of taught it is you find your MRS, right, which is 2 over 1. And because we don't have diminishing marginal rate of substitution, that means that we're going to have a corner solution, right? So our x1 and our x2 axis right here, right? We know that we basically have a fixed isoquant, right? So we could either have 50 units of x1, and that'll get us to 100 units of production, or we could have 100 units of x2, and that'll also get us 100 units of production, right? So we know that with perfect subs, we have a linear line right here. And so kind of like any other like just consumption question, right? We basically just do, yeah, you could do the bang for your buck method, or you could just compare your MR, or see, it's even kind of bad. I wrote MRS and I meant TRS. That's how much they're very similar to each other, right? We know that our cost ratio is equal to 5 over 2, right? And so this is basically our cost ratios means that we're going to have isocosts that have a slope of 2.5, right? And so we want to see which puts us on the lowest. So in this case, we want to be on the lowest cost ratio, right? And so we know that this is going to be the lowest point, right? As opposed to here. We don't want to be here. We want to be here because this puts us on the lowest cost ratio. So we consume x2, right? Because of the fact that we know we're going to need 100 units and they each cost 2. So this is equal to 200. Whereas with x1, it would be consume 50 units, but they each cost 5. And so this would be equal to 250, right? And so this is lower, right? Which means that it's where we want to be. Okay. That's kind of it for now. If you guys still have questions, you're more than welcome to ask. I'm going to be here through like 2 o'clock, and then I'm going to switch to my drop-in. Or if no one hangs around, I'll just switch straight to my drop-in.
So for this substitution problem, when we just find our optimum point, which item we want to use, we just multiply the price of that factor by the amount of units that we were given, right? And then that should.
Yeah, honestly, that's probably an easier way of doing it with these questions is just see how many units you need to get to 100 and just multiply that by the price, right? But both methods work. There's multiple ways of getting the right answer. It's just whatever you're comfortable with. Okay. So I'm going to stop recording.